Good morning and welcome. I'm Daphne Richards, Travis County Horticulture Agent with the Texas A&M AgriLife Extension Service. Thank you for joining us for this webinar and our Water-Wise Strategies for Austin Gardens series. We've got a great program lined up for you today, irrigation and smart controllers. As part of this program, our presenter may refer to various source material or websites. Don't panic if you don't catch those in time to write them down. All registrants will receive a follow-up email chock full of great stuff, including a link to the recorded session and links to any references or resources listed. Today, we'll be taking some questions when we break, as well as at the end of the program. To pose a question, you'll need to use the Q&A feature. Simply type in your question at any point, and we'll address them at 2 times, during our mid-program break and at the end. We'll get to as many questions as we can, and we'll follow up after the program on any that we run out of time for. Our presenter today is Charles Swanson. Charles is a state of Texas licensed landscape irrigator and has over 12 years experience conducting statewide trainings and short courses for irrigation professionals, municipal employees, and state agency personnel in landscape irrigation and water conservation. And he does so with the Texas A&M School of Irrigation. He currently manages the daily operations of the Texas Evapotranspiration Network, the Water My Yard program, and coordinates various testing and evaluation programs for landscape irrigation products such as sprinklers, drip irrigation, and smart controllers. We're going to be hearing a lot about all of those today. I'm excited to have Charles with us today. So without further ado, Charles, the stage is all yours.
Good morning. Thank you for having me today. Today, I'll be speaking about irrigation and smart controllers. So, as a quick overview to irrigation, if you look at the current state of irrigation technology today, we can break landscape irrigation technology into 2 basic categories. We have what's referred to as irrigation control technology, which manages how and when we irrigate. And then we have irrigation application technology that manages how the irrigation water is applied. For today's presentation, we're going to focus on irrigation control technologies. Different types of irrigation control technologies include not only smart controllers, but sensors that can affect controller operation as well. With smart controllers, we have 2 basic categories, which include weather or ET-based controllers, as well as soil moisture-based irrigation controllers. Sensors can be attached to these controllers that affect their operation. It can shut off irrigation during times of rainfall, irregular flow, or other site-specific conditions. Today, we're going to focus primarily more on weather and ET-based controllers in the smart controller market. Just to review, when we look at irrigation technologies as far as application methods, we have drip irrigation technologies available. We have high efficiency sprinklers and pressure regulation of irrigation sprinklers that affect how we apply water. So to start out the day, we're going to have a pop quiz pop up, and we're going to do a poll and ask you a question of how much water do Central Texas landscapes need, and particularly turf grass during the summer. Okay, so we'll come back to this question here if we get through this next section and see if you had the right answer or not. So let's find out. So what effect does the climate have on watering requirements? So climate plays an important impact on how much water our landscapes need. We can refer to the current U.S. drought monitor, for example, and that can give us a current state of what the climate has been like regionally and recently. So you can see here, if we look at currently here in the Central Texas area, we can see that the Travis County area is experiencing some abnormally dry to moderate dry to extreme dry conditions in this area. And so this was taken last Thursday. Every Thursday morning, this drought monitor is updated. If we compare this to where we were last summer, at the beginning of August, which is our peak irrigation season of the year, we see the complete opposite conditions occurring in the state. At that time, 94% of the state was drought free, and there was no drought conditions occurring in Central Texas. So historically, this time of year, as we move into the summer months, we can see that we could be experiencing some level of drought, or we could be in good condition, showing that we've received ample rainfall. So if we look at the last 4 years, 2021 to 2018, we can see here a couple of the years have shown some drought conditions, and then a couple of years have shown no drought conditions. So climate is always changing, and depending on how much rainfall we're receiving, that tells us how dry our landscapes are and do we need to irrigate or not. So how do we determine how much we need to irrigate, if any? Well, in irrigation, we use evapotranspiration. Now, evapotranspiration is a big word, but it's actually made up of 2 words. It is made up of the word evaporation and transpiration. So with evapotranspiration, or ET, as we typically refer to it, we measure the amount of water that evaporates from the soil surface and that is transpired by the plant. So if we combine these two terms for a site, we can use this to determine the total water requirements of various plants and crops at a specific location. And we typically measure this in terms of how many inches per day a plant needs. Now, while ET is very difficult to measure directly and requires specific field equipment, it can be calculated using weather data. There are multiple methods out there for calculating ET using weather data, the most common being what's referred to as the Penman-Monteith equation, the Hargreaves equation, and the Blaney-Creel equation. However, most researchers agree that methods that use solar radiation in their calculations have proven to be the most accurate. The Penman-Monteith is a solar radiation-based method, and it is referred to as is our standard method used by most researchers and scientists that study plant water requirements in irrigation. There's actually an international standard on reference evapotranspiration published by the American Society of Civil Engineers that most use today for calculating ET, and it is considered one of the most accurate methods used. Now, just to give a background on ET, what happens when we calculate ET? Well, calculating ET with the Penman-Monteith equation, for example, calculates what's known as reference evapotranspiration, or ETO. To calculate ET, we have to know a lot of information about a plant. We have to know how tall it is, the size of the leaves, how dense it covers the soil surface, lots of specific details for each individual plant. So to make this simple, what scientists do is they calculate ET for a reference plant. And we use that reference plant to then determine how much water all other plants in our landscapes and the fields need. So when we calculate reference evapotranspiration, or reference ET, what we're actually doing is we're calculating the ETO of the water requirements of a cool season grass growing 4 inches tall under well-watered conditions. So we use a grass reference, but we use a cool season grass reference that is very similar to a fescue grass, because fescue can be grown globally. So researchers like using that plant, and they can share data between research projects. Now, to calculate reference evapotranspiration using this method, we need to know specific local climate data. We need to know information about local solar radiation, and this is how much energy we receive from the sun, ambient air temperature. We need to know about the local humidity or dew point temperature that tells us how much moisture we have in the air. And we need to know some information about the wind conditions that we refer to as wind run, which tells us how much wind we receive per day. You can think of this as how far does the wind blow over a certain 24-hour period. And we can measure this information using standard weather station sensors. So we have weather stations that have temperature relative humidity sensors. We have anemometers that measure wind speed. We have pyranometers that measure solar radiation. And then we'll also have a rain gauge on our weather stations that help us in irrigation scheduling calculations, but rainfall is not a part of the ET calculation itself. So if we're going to calculate ET, we need to have a local weather source that measures these 4 parameters: temperature, relative humidity, wind speed, and solar radiation. Here are examples of typical ET weather stations installed in both agricultural and landscape sites. Now, the ET equation is a little complicated. Here's the Penman-Monteith equation, for example. And so it's actually made up of 9 different parameters that you have to calculate to input into the Penman-Monteith equation. So most people are glad we have computers these days because we don't have to calculate this by hand, but it is a rather complicated equation if you have the correct data to input. And so you can see here that each parameter of that equation requires a calculation taking into account those local weather conditions for temperature, humidity, solar, and wind data. So if you're interested in ET, you can look up, and there's lots of resources online talking about the Penman-Monteith method and how we use it. Here's some of the numbers we use as part of that equation. And what's important to reference here is we can see here, these are all specific parameters fixed in for use with grass reference plants, such as our fescue. Now, we have a lot of faith and confidence in this method because it's been around for a very long time. The Penman method was first published in the 1950s by a British scientist named Penman, and researchers have spent careers studying ET. One of the leading ET research facilities in the country is actually located in Texas at the USDA ARS Conservation and Production Research Laboratory, which is located in Bushland, Texas. And you can see here, this is actually a solid field of fescue grass that has a weather station on top of it. And then inside that field of fescue grass, we have these giant weighing lysimeters, which measure the differences in mass of the soil, the weight. And so we know as the plant uses water, we lose water from the soil, and these giant scales underground measure that. And we can compare that to the equation and verify that we are measuring the correct amount of water being lost from a site. So lots of research goes into this, and we have lots of confidence in this approach. Okay, now when we use ET and reference ET, like I mentioned earlier, that is calculated using a cool season grass like a fescue. Well, in Central Texas, you probably do not grow fescue in your yards. You're going to grow something else. So how do you determine how much water your plant needs versus that fescue? Well, we have to have a vision. Now, we have to understand that a lot of the science of irrigation was developed for agriculture, and it has been translated to be used in landscape irrigation. So a lot of these terms still carry over. So you may also see this referred to as a plant coefficient, a turf grass coefficient, or even a landscape coefficient. But the important thing is that for whatever plant we are going to irrigate, you have to know what the coefficient is for your plant to calculate its water requirements. And the coefficient is nothing more than a percentage of water use compared to ET of our reference plant. So we look up how much water our plant uses compared to our reference plant as a percentage value. So if we look at turf grass, for example, most of us have turf grass in our yards. We spend lots of research is spent on studying the water requirements of turf grass. And we can see here are some common coefficients for turf grass fields. We have warm season turf grass, so plants like Bermuda, St. Augustine, zoysia are warm season grasses. They have a peak crop coefficient of 0.6 or 60% of our reference ET. Cool season turf grasses, like you may overseed with ryegrass your yard in the winter, has a higher coefficient, which means it uses more water. It has a coefficient of 0.8, or will use 80% of what a reference plant will use. And then if we look at sports fields, sports turf, that's highly maintained, high level of management where it's mowed very short, and it's played on for sports fields like baseball fields, soccer fields, football fields. Those type of facilities will have a coefficient of 0.8, even if they are warm season grasses, just due to their level of management. So lots of factors go into determining a plant's coefficient. In agriculture, we could have multiple coefficients for a plant because we plant a seed and then that plant emerges and it slowly grows, it becomes taller, takes up a larger surface area, and then it produces a fruit or a grain, and then we harvest that. So at each major growth stage, that coefficient changes. And so things like the plant density, quality, level of stress, all those factors influence the coefficient. However, with most landscape plants, we're not really actually growing the plant. More often we're maintaining established plants. So in most cases, we have a single coefficient for established plants in our landscapes. Now, there are many different types of plants we could have in our landscapes. If you just visit any local nursery, you'll see there are dozens or hundreds of types of flowers, shrubs, trees available for you to plant in your yard. And so we haven't been able to research every specific variety of those plants to get each variety specific crop coefficient. But what we have done is we've grouped these type of plants into different categories. And based on its watering group, we can assign it a crop coefficient or a plant coefficient. So the three basic categories we have for non-turf areas are frequent watering areas, which is going to take up most of our bedding areas for our flowers. We use a coefficient of 0.8. Occasional watering areas are ground covers, vines, and small shrubs that require less frequent irrigation, but typically have deeper root zones. These plants typically use a plant coefficient of about 0.5. And then we have natural rainfall plants. So these are plants that once established and we get average rainfall conditions, really do not require very much supplemental irrigation until we get into extended dry periods. So in these plants, we're talking about large shrubs or large established shade trees that will have a coefficient of 0.3. Now, in irrigation and agriculture, our goal is always to achieve the highest crop yield. Farmer wants to irrigate his field so he gets the most crop to harvest. Well, in landscapes, if we were to compare that to a landscape situation, it would be like, how often do you want to mow your yard? If you give your lawn more water, it's going to grow faster. You're going to mow it more often. So what we try to do in landscape plants is not try to grow plants as if we were trying to produce them for production value, but to maintain them for their aesthetic value. So what we can often do is induce some type of allowable stress on a plant to maintain an acceptable plant quality, where we reduce our water usage, but then we maintain a nice visual aesthetic plant. And when it comes to turf grass, research has shown that we can actually cut back our water usage on typical turf grass landscapes by as much as 40% and still maintain nice green grass that doesn't require being mowed as often. So here's a typical adjustment factor scale we see used in turf grass landscapes. So if you had a very high quality landscape that was very frequently, it was aerated, heavily fertilized, things like a sports field or a park area, you probably want to have maximum quality turf grass in those areas for those purposes. But if you just want to keep a nice green grass in your yard that looks nice and you're not out there having to mow it more than once a week, you'd probably want to have something like a normal quality grass. So you can induce a 40% reduction or use an adjustment factor of 0.6 to reduce our water usage. That helps conserve water, but we maintain nice green grass. So how does this all come together? Well, at this point, it becomes pretty simple math. Calculating the water requirements of our plant, once all we have to do is look up our parameters. We can look up our ETO based on weather data. We determine what our plant is that we're irrigating. We've gone through the different plant coefficients for turf grass and landscape plants. And then we determine, do we want to induce any type of adjustment factor to reduce the amount of water we're going to use at our landscape? And all we have to do then is multiply these factors together. Simple multiplication to determine how much water our plants need. So let's work through a simple example here. So if we look back at last summer for this example, I looked up that the second week of July in Austin, the ET was 1.24 inches. That was calculated from weather data. And in a little while, I'll show you where we can look up this information to find out what the ET is for your area. So the ET for the Austin in the second week of July was 1.24 inches. If we have a warm season turf grass lawn, such as Bermuda, we would use a coefficient of 0.6. And like I mentioned, we can typically reduce our water requirements by 40% to maintain nice acceptable green grass that uses less water and requires less frequent mowing. So we multiply these factors together, 1.24 inches of ETO times 0.6 or 60% coefficient for warm season turf grass times 0.6 or 60% adjustment factor for normal plant quality. And we can see here that for the second week of July, the water requirement was 0.45 inches for that week. Now, where does rainfall come into the picture? Okay, rainfall is not calculated as a part of the ET calculation. What we do is we use rainfall as a part of the scheduling process. We calculate how much water the plant used, and then we determine, was any of that water replenished based on any rainfall? And so when we look at it when it rains, obviously not all rainfall every time it rains is going to be used by the plant. If we get heavy rainfall events, some of that water could run off, or if we get a very light rainfall event, that most of that water will evaporate before it could actually infiltrate into the soil. So we have to take into account some level of judgment when it comes to looking at effective rainfall amounts. So here at the bottom is one simple scale that's often used for landscapes to determine how much rainfall should you take credit for. And so in this simple scale here, we can see here that we ignore the first 1/10 of an inch of any rainfall event because that water usually evaporates rather quickly. We can take, in most cases, full credit for rainfall that occurs between 0.1 and 1 inches. We can take about 2/3 credit for rainfall that occurs between 1 to 2 inches. And then whenever we get over 2-inch rainfall events, a lot of the water after that 2-inch rainfall mark is going to typically run off of a landscape. So we usually do not take very much credit or any credit for that rainfall after that 2-inch mark. So let's go back to our example here from July. And we can see here that that second week of July, our weather station only recorded 0.01 inches of rainfall. So since less than 0.1 inches occurred, we assume no effective rainfall. So there's nothing to subtract out of our water requirements. So our plant still requires 0.45 inches of water. Okay, so if our plant requires 0.45 inches of water, how do we actually apply that water to the landscape? So we know how much water our plants need. Now we need to create an irrigation schedule. So we'll take a few moments here and review the basics of irrigation scheduling calculations. So how do we determine how often we should irrigate? Our initial calculation told us how much to apply, but didn't tell us how often. So what affects irrigation frequency is going to be our soil type and the depth of our root zone. When it comes to irrigation scheduling, our goal is to wait until the plants have used up all the water in the root zone, and then we irrigate to refill that root zone back up. This is very similar to the gas tank on your vehicle. You put so many gallons into your gas tank, and then based on how far you drive, you use up so much gas. So when you refill, you only fill up the tank what you've used up. You don't apply any more than what the tank can hold. Typically, we do these calculations on a 7-day or weekly basis. So this process starts with first determining how much water can be held in the root zone. Once we know how much water can be held in the plant's root zone, then we can determine, do we need to irrigate one or more times per week based on how much water our plant is using. So here's some common scheduling terminology when it comes to determining how often we should irrigate. Plant available water refers to the amount of water in the root zone of a plant. The effective root zone depth is used to determine what depth into the soil contains 80% of the total root mass, which is where the majority of the majority of the area the plant pulls its water from. Soil water holding capacity refers to the amount of water that can be held or stored in the soil. And then we also look at managed allowable depletion, which helps us determine how dry do we let the soil get between irrigation. And again, this is simple math. We look up our values and become simple multiplication. We measure how deep our roots are in our landscape. We can look up in charts the water holding capacity of our soil, and then we determine how dry do we allow the soil to get between irrigations. We multiply all those together, and that will tell us the total amount of water available to our plant. So like I mentioned, effective root zone depth. We're primarily interested when we look at the root zone, what depth into the soil contains 80% of the total root mass. This is where the majority of the water will be pulled from. We try to exclude those very deep tap roots or those feeder roots and look at where that main mass is located at. And in most cases, this is very easy to measure in your yard. If you have a shovel or a soil probe, you can go out there and take a little plug sample out of the ground and measure how deep your roots go. So here's an example. I'm using a soil profiler here. This is what this is called. And I push it into the soil and we pull out this large plug of soil here. And it allows us to examine two things. One, we can break this up and we can see how deep do the roots go into the soil. And so we can see here we have multiple roots and we can measure that using a ruler or a tape measure. But then it also allows us to look at and see what is our soil type that the roots are traveling in, is stored in. Now, some of you probably looked at that picture and thought that's impossible in my yard. And so if we have a reality check in, Central Texas, many landscapes around Central Texas do not have very deep soils. And so it's very common that in many landscapes in the Austin area, you'll have a very shallow root zone just because we do not have very much soil on top of the impervious layers like the rock, the caliche, and those other dense materials. So having very shallow soils makes it very difficult to encourage deeper root growth because there's not a lot of area for the roots to expand and grow into. Managed allowable depletion. Typically, we just refer to that as MAD in irrigation. Helps us determine how often we need to irrigate when we are looking at no restrictions in place. Okay. What MAD does is it allows us to manage how much water is still in the soil each time we irrigate. You don't want to always use up all the water in the soil between irrigations. If you use up all this water in the soil, then your plant hits its wilting point. And we can see that those plants then wilt, they don't look very nice in our yard. So, and sometimes it's not very healthy for those plants to frequently become wilted and then revive back and forth a lot. So what our goal is, we always want to try to keep some water in the soil between irrigations so that we never stress our plant to the point where it actually begins to wilt. So we always keep a little bit of water in the soil as a reserve, and then we irrigate what the majority of what the plant uses. This is very similar to thinking about going back to our gas tank analogy. You have your gas light in your car. You don't wait till you use up all the gas in your gas tank because then you can't get to the gas station. You have a certain point where you say, oh, I need to get more gas. So that gets you back to the gas pump to where you can refill up and you're not left dead on the side of the road waiting for someone to bring you gas. So maybe that'll help you understand this concept. So how much water can be held in a soil? Different soil types have different water holding capacities. So we know sands hold less water than clay soils. So here in this table, we can see here how much water can be held in a foot of soil, so 12-inch depth of soil. So at field capacity, we can see here a sand can hold between 1 to 1.4 inches, but then at wilting point, there's still about 0.2 to 0.4 inches of water in the soil, which means if we subtract the field capacity from the wilting point, that is our water holding capacity. That's the amount of water we typically use between irrigations or have available for use for the plant to irrigate with. So you can see here that a sandy soil, typically we get somewhere around 1 inch of water storage for every 1 foot depth into the soil. Compare that to a clay soil, we can see clays have very high water holding capacities. We can see here at field capacity between 3.5 to 3.9 inches of water, but then at wilting point, when the point where the plant can no longer pull the water out of the soil, there's still about 1.5 to 1.7 inches of water being stored. So if we subtract the field capacity and the wilting point for a clay soil, we can see we have about 2 inches of water per foot to work with in the soil. Now, if we only allow ourselves to use half that water so that the plant never goes into any signs of stress, never wilts, then we limit ourselves to half that water. So we can see here in most landscape plants, conservatively what we use is a value of 50%. We use 50% of the water available to the plant. Once that's depleted, then we irrigate to refill what's been used. Always keeping some of that water in reserve storage there so the plant never goes into a wilting state. So you can see if we're looking at sand per foot of soil, we're only looking at about a little less than half an inch, 0.45 inches. And then with a clay soil, about 1 inch of water per foot of soil. So we break this down for different landscape conditions. And we can see here, this is a simplified chart that we just looked at. So most landscapes in Texas have clay soils. So we'll focus on the clay row here. So if you only have 2-inch deep roots in your landscape, that means you only have 0.18 inches of water available to your plant. If you have 4-inch deep roots in the clay soil, that means you have 0.35 inches of water available to your plant. So deeper roots means more water available. And then we can move further one more step, and we can see here at 6 inches, that gives us about half an inch of water available to our plant. So let's go back to our earlier example for our Dallas residents. Okay, say that we have a residence and we go out and we measure in our yard where we have our grass, the roots are 4 inches deep. And in that process, we also determine that we have a clay soil. So how do we determine our irrigation frequency or how often we need to irrigate? Well, all we have to do now is look at from our tables, our water holding capacity, and then we can calculate how much water is available to the plant. So from our previous tables, we know that a clay soil can hold 2 inches of water per foot of soil. The only thing we have to pay attention to when we do this calculation here is our units. Make sure that we refer to everything in the same units. So here we're looking at inches of water per foot of soil. Well, the roots go into the soil. So our root depth and our soil depth should always be in the same units. So in this case, if our roots are 4 inches long, we need to convert that into feet so that it matches the same units. So 4 inches is the equivalent of about 1/3 of a foot. So again, it's some simple math. We just do some multiplying. The depth of our root zone, how deep our roots go into the soil in feet. We said about 1/3 of a foot, which is the equivalent of 4 inches. We look up our soil water holding capacity. We saw that for a clay soil, we could hold about 2 inches of water per foot of soil. And standard practice is to use a managed allowable depletion of 50% or 0.5. This is saying you're going to use half the water in the soil and then leave half of it in reserve. If you have very drought resilient plants, you could actually increase this value. But some plants, if you increase it too far, you will start to observe some signs of early wilting stress occurring. So plants that are very sensitive to water stress, you would not want to increase your MAD. Plants that are more drought tolerant, you could potentially increase this a little bit more. But on average, about 50% works well. So 0.33 feet deep long roots times 2 inches of water per foot of soil in our clay soil times allowable depletion of 50% or 0.5 means that we only have 0.33 inches of water available to our plant between irrigations. That we're only going to allow ourselves to use and store 0.33 inches of water in the soil. Okay, so how does this all start to come together? Well, if we recalculate that for the second week of July, based on ET, the evapotranspiration of our warm season grass, that we need to put out 0.45 inches this week, but our soil can only hold 0.33 inches of water between irrigations. That means we're going to have to fill the soil up twice between irrigations, or twice per week. We're going to have to irrigate that soil to make sure we have that 0.45 inches of ET that's being used up available for that plant. Now, this is how we typically use the science of irrigation scheduling. Unfortunately, irrigation frequency can be influenced by other outside factors, such as local ordinance water restrictions. So in the case of water restrictions, it really limits our ability to produce a good science-based irrigation schedule. Water restrictions are in place to help conserve water and help manage the water load on the utility in the city. So we'd always give the plant all the water it needs. So if you don't have water, if we have water restrictions that limit us to only 1 day a week, for example, or 1 day every other week, severe water restrictions, what we end up doing is we have to increase our MAD. We're going to open up how much water is available to the plant. And basically, we're going to be using up all the water in the gas tank between irrigations. We fill up the gas tank, and then if we have to wait so many days, no matter what, before we can fill up, we fill it up and we wait until we can fill it up again. And the plant has to survive off that amount of water until it rains or restrictions don't exist anymore, so that it can get more water to reduce that level of stress. And so when we do have water restrictions, we do need to learn to adjust our schedules to only irrigate to the capacity of the landscape. Going from 2 day a week to a 1 day a week restriction doesn't mean we double our run times or apply more water. We can still only apply so much water that can fit in the soil. So we need to take that into account and don't over irrigate during these times of restrictions. Only irrigate to how much water you can hold in the root zone of your plant for your soil type. Again, like I said, this can be a challenge for many Central Texas landscapes because Austin area, depending on where you're located at in Travis County, for example, you could have very shallow rocky soils, or you could have very deep soils, depending on what edge of the county you're in. And so if you have very shallow soils, that means you're not going to have a lot of ability to store water in the soil. Typically, shallow soils do require more frequent irrigations because we cannot hold that much water. So we will see landscapes that have shallow soils have more drought stress occur during the peak of the summer because we don't have the ability to put out enough water or store enough water between irrigation events. So we can see here, very shallow soils here, and here we have a Central Texas landscape that doesn't look the greatest. It's being irrigated, got some green grass, but the very shallow soil means there's not a lot of water available, so it's going to be a little bit more stressed at the peak of the summer, but probably in the spring and fall, it'll probably look pretty nice. So promoting deeper roots increases the drought tolerance of our landscapes by increasing the amount of water it has available for the plant to use. Historically, And statistically, really, if we have landscapes with 6-inch deep roots, we can survive the majority of the year with 1 day a week restrictions with very minimal stress at the summer peak. So if you have a very shallow soil, you could bring in more topsoil to increase the depth of your root zone. That'll help. And like I said, 6 inches works very well for majority of the year. You'll only probably have a 2 to 3 week period in the summer where you'll see the peak of your plant stress, but then the rest of the year, your plant will survive just fine off being able to store the amount of water in that depth of a root zone. So what we can see here is if we look back at our earlier table here, and this time we take away MAD. So we look at this as purely a function of how much water is really held available to the root zone in the soil, using all the water between irrigations here. We can see that if we have a sandier soil with a 6-inch root zone, we can have about 1/2 inch of water available for the plant for the week. If we have a clay soil and we have 6-inch deep roots, we have about a 1 inch of water available to that plant for the week. Going back to our earlier example from the second week of July, we can see here that even with 4-inch deep roots, if you take away MAD at the peak of the summer, we have about 0.6 inches of water available. So there is enough water to go irrigation week, 1 irrigation 7 days to 7 days throughout the summer. But towards that last day of the week, you could see a little bit of stress before you irrigate start to occur. Okay, so where do we find the data to do these calculations? I don't expect, most people don't go through and do these calculations themselves. We have some type of a tool to help us do this. So where can we find ET data and what tools exist to help us do these basic calculations? Well, the best resource I have available for most people is the Texas ET network. And so you may want to make a little quick note of this. It's just texaset.tamu.edu. There's no www. And this is an AgriLife Extension project. The Texas ET network is comprised of over 90 weather stations around the state that exist for the sole purpose of calculating ET. So like we said earlier, what do we need to know to calculate ET? We need to know temperature, humidity, solar radiation, and wind. And unfortunately, not all weather networks record those 4 major parameters. And so if you start looking at different weather networks, most will have temperature, most will have wind, some will have some level of degree of humidity or dew point temperature, but not many weather networks report solar radiation. And so that's really what distinguishes many weather networks from ET weather networks is the fact that they record solar radiation. Also, a major difference in weather networks between ET stations and non-ET stations is that an ET station needs to be in a landscaped area over a grassy surface. So like you saw in my earlier pictures, it's in a field or it's in a landscaped area. We don't want to have a weather station on top of a building or in the middle of a parking lot because that creates heat island effects where we get heat absorbing off the concrete or asphalt or rock surfaces where it makes the local temperature around the sensors much hotter than what the plant environment is. So we use so we have special networks with special sensors to help us do this. And so we can see here, there's a map on the bottom right corner of our density of weather stations in the state of Texas. Like I said, this is a project. So most of these weather stations are owned by private entities or private and public entities. This is a program that myself and Dr. Guy Phipps manage through AgriLife Extension, and we only own 2 of the 90 weather stations. All these other stations are owned and sponsored by other entities who need ET data, and we help them collect that data and do these calculations for them. So to give you a better view of general central Texas, we have these weather stations here in the greater Austin area, Travis County, and surrounding areas. We can see Round Rock down to Buda, down to Cedar Creek, up to Spicewood area, Marble Falls, Burnett area as well. Majority of these stations are actually sponsored and owned by the Lower Colorado River Authority as a part of their HydroMet network. And then a couple of these stations are a part of the new Texas Mesonet network. So I'm going to pull up an example here, going back to a summer example. And we can see that from that example we did earlier in our slide set in Austin, this was that 7-day weather summary that was used to calculate that the ET for that example. So you can see here the temperature data, the humidity, solar radiation, and the wind data. And then that is used to calculate each day's ET, or reference evapotranspiration. And we can see there, that's where the 1.2 came from in our example, the 7-day ET from that weather station in Austin. Now, we do have calculators here on the website to help us do these calculations for us. I've gone through and given you some detail on the background of these calculations, but you can go to the ET Network website and you can do these calculations using the tools on the website. So we can see here, we look up the ET for our location. We could actually specify how many days of ET is used in our calculation. So 3-day, 5-day, 7-day, or 2 weeks of data per calculation. We can choose our plant type. So in our example, we did warm season turf grass. We can choose an adjustment factor. We said normal quality grass. And again, we had less than 1/10 of an inch of rainfall occur. So we can calculate how much water is needed. If you know how much water your sprinklers apply, the precipitation rate of your sprinklers, you can then use the calculators here to calculate your irrigation run times. If you like this calculation method, you actually can go online to the Texas ET Network, and we have an option for you to create user profiles. So go to the user account. I'll actually go back a couple of pages here. You can see here in the top right corner of the Texas ET website, you can see here we can create a profile, or there's a link here at the top to why create a profile. That'll take you through the steps to create a site where you pick a weather station, you pick what plants you're irrigating, you pick how many days of weather data to use, and then you pick a notification day. And then on that day, you can get an email that will tell you how much water your landscape needs. So here's an example of an email I got this week for our research plot here in front of our office building here on campus in College Station. So you can see here, we have the daily ET, the temperature and the humidity, the solar radiation, and the wind speed data from that weather station here on campus. It tells me that my plant used for my plant type, I have warm season grass, adjustment factor of 0.6. I did get some rainfall, so I got 0.7 inches of effective rainfall, but my landscape still needs about 0.19 inches of irrigation. So even though I got some rainfall, it was not enough in this case to meet 100% of the plant's needs. So I will know I need to go out, irrigate about 2/10 of an inch on my grass for the next 7 days. The ET network also has historic data. So if you want to look at the historical trends of ET, we can see here for 19 cities in Texas what the historic average monthly ET is for each site. So we can see here for comparison purposes that in Austin, the ET peaks pretty close in July and August. We can see here 7.22 inches per month to 7.25 inches in August, very close. So right now we just started we're the early part of May. So for the month of May, it averages about 6.39 inches per month. And then we can see how that'll increase through the summer. And then ET typically drops then significantly in September into the fall. You can also compare that to long-term average rainfall data to see, how much rainfall can we expect historically on a monthly basis. So we are behind on rainfall. We can see here that April and May are some of the higher rainfall months of the year. And we aren't getting exactly that much rainfall right now. So we are below average on rainfall currently. So we go back to our poll question earlier. I asked you, how much water do Central Texas landscapes need in the summer, in particular our turf grass? So what I have here is I have graphed up the ET for the it's the 8 weather stations in the greater Austin area, Travis County area from last year, 2021. So we're using a year of last year's data. And we can see here that the ET, this is weather station ET, does vary a little bit from site to site because at all locations, the climate is not always exactly the same. If one part of the county was cloudier, then that means you got less solar radiation. Maybe one part of the county was hotter, got more wind speed. So any changes in weather conditions affect that daily ET calculation, which then changes how much water is required per week. So we can see here the ET per week in 2021 peaking here in July and August. Now to calculate how much water would grass need, we need to multiply this times our crop coefficient and any adjustment factor. And we can see here that when we do our calculations for last year, we can see that in 2021, for example, we actually peaked at about, Austin area peaked at about 0.65 inches per week. Okay. And if you remember, last year was a rather mild year. We typically got more rainfall in 2021 than we've received this time this year. So last year, we never hit the 1 inch mark in Austin. Okay. But the majority of the summer months, we can see we were actually somewhere around the 0.5 to 0.6 inches of water per week category or range. Obviously, here in the early spring, spring moving into the summer months, we have some fluctuation in our early hot period to our cooler periods coming back and forth as we had different fronts occur. We can see different changes occurring, usually building up, like I said, to about that 0.5 to 0.6, depending on what part of the county or Central Texas you're located in. So not all land, we see often people use the term an inch of water a week, but on average years, we actually don't hit that 1 inch of water per week needed in many cases. And so this is why it's very important to pay attention to the local climate and only apply the amount of water you need. Because if you put out an inch of water consistently all summer, you're going to put more water out, and that's wasted water that could be used later on when restrictions are in place or water supplies are more stretched to where you could use that water later on in the future. Okay. And so just going back to the weekly summaries here, here's that same data posted in a table format. And what I want to highlight here is this was the weekly calculations here for those weather stations. So if you had a email you received from Texas ET that told you, each week how much water you need, and if you need to irrigate, yes or no, would be a good summary of that. And so based on 2021 data, I'll highlight Austin here. In 2021, the weather station ET was 40.62 inches, and our weather station recorded 35 inches of rainfall. So you almost got more rainfall than what the ET was, which is good in terms of water conservation. And so by the time you do your calculations on a weekly basis, last year, you only needed 6.3 inches of water for turf grass in Austin. That's what our calculations showed. And if we look at that on a weekly basis, that's only 20 weeks of the year. 32 weeks of the year last year, you did not have to irrigate because you received enough rainfall to meet that plant's weekly water requirement. And that's what we often find in most cases, that you can save you don't have to irrigate on average about 30 weeks per year. We can see here looking at many of these locations here across greater Central Texas. It looked like Spicewood was no irrigation. Marble Falls, 28 weeks, so a little bit outside the Austin area, but No irrigation was needed 28 weeks there, but then we can see here between Lakeway, Dripping Springs, Burnett, and Buda, no irrigation was needed 34 weeks. So turning off your irrigation controller because you got enough rainfall over that 7-day period that your landscape did not require any supplemental irrigation. Okay, so with that, I think we're going to hit our halfway point and we'll stop and take a break. I'll turn it over to Daphne.
Yes, thanks, Charles. Let's take a break for about 3 minutes. We'll come back sharply at 10:59. All right, everyone, welcome back. Wow, Charles, such really great but pretty dense information. So before we dive into some questions, would you just kind of distill some of what you said for the layman, people maybe who are confused by ET? What's kind of like the main point you'd like for people to understand from what you've said about just how much water plants need, irrigation systems, before we hop into the smart controller part of this?
The important thing is I would like to convey is that water requirements change throughout the year. And so we know we've observed lots of people do a really good job of managing their irrigation at the peak of the summer. They see their lawn is stressing, they'll put out more water as needed at the peak of the summer, but we typically peak only over a short period, about 3 to 4 weeks. We don't have to irrigate at that high volume year round. And so what ET does, it makes it an easy way for us to see where are we in the process of plants increasing their water use. We're at a minimal point, or at the middle point, or at a high point. And if we can use some type of weather monitoring system to adjust our schedules to where we're not putting on an extremely high amount of water continuously, we can save water, and it also saves you money because your water bill goes down early in the season.
Yeah, I really like that point. And I found it noteworthy that we need to remind people about the generalities that we have to use when we're speaking broadly. So as you pointed out, we always say your grass needs 1 inch a week of water, which it does, but that doesn't mean that you have to apply that entire 1 inch if we've gotten any rainfall, or if the soil has not evaporated away so much water that 1 inch is missing. So that was one point that I really wanted to stress. All right, well, someone has asked, how far down did your tool dig into the soil? What was the soil depth on that?
On the picture I showed?
Yeah.
I believe that profiler digs down 8 or 10 inches.
Wow, that's pretty deep, but it's good to point out that especially turf grass, the roots grow down that deep. So we've got moisture down in there. The plant is able to take advantage of that moisture.
Absolutely, yes.
Yeah. And one more question before we dive back in. Does fertilizing your turf influence how much water it needs?
It depends. It's a trick question. If we're talking about, just an annual fertilizer, you fertilize early in the spring, it doesn't. You still continue to irrigate as normal because you're maintaining a certain acceptable plant quality. Now, if we look at highly maintained fields like sports fields, they fertilize multiple times per year, and so they're trying to maintain a certain growth rate to maintain vigor and density for certain purposes. And when you're fertilizing for that purpose, then your water requirements can increase by as much as 20%, just because you're encouraging that much faster growth in the plants.
Well, you've used one of our favorite phrases that we use around our county office, and that is, it depends. Isn't that true of every answer? Thanks so much, Charles. All right, let's dive into smart controllers.
Okay, thank you. Okay, so we had to understand how scheduling works, because when we talk about smart controllers, we've learned that smart controllers aren't all the same, and they all operate differently in how they manage how much water they're applying. So now we have a basic background understanding of how irrigation science is supposed to work. We can then move into a discussion of how do smart controllers work, and do they do all this for you automatically? So what is a smart controller? Well, today we're going to focus on weather-based, ET-based controllers. And we're talking about irrigation controllers that determine the run times for their individual stations based on historic or real-time ET with additional site-specific data. And so our goal with the use of a smart controller is that it's going to adjust our irrigation schedule as the weather and the seasons change. So we saw how ET can vary from January to the summer into back into the winter again. We would hope that a smart controller would adjust its water requirements and only put out a little bit of water in the spring, put out more water at the heat of the summer, and then reduce how much water it applies then back to the fall and winter. And so smart controller technology, it has greatly improved over the last 15 years. We started formally evaluating smart controllers in our program here back in 2007. And there's been a huge shift in technology over that period. And during that time, we've seen multiple controllers come and go, and manufacturers release different models and series, continuously improving on the technology. And so with that change in technology, we've seen many people question performance or struggle to determine which one is the best. And there's multiple programs out there that have been evaluating smart controllers for a while. And I'm going to talk about that a little bit. And so just to start out with some background, I just want to give a few moments to discuss the EPA WaterSense program. And some of you may be familiar with EPA WaterSense. It's a partnership program of the US EPA. That's goal is to identify water efficient products in the marketplace, and those products that are at least 24% more efficient in their water use than comparable products without sacrificing performance. And these products have been around for decades, early 2000s. Some of the earliest products we know are the toilets. They always had that little blue-green sticker on the corner saying WaterSense meets EPA criteria on them. That slowly evolved from toilets to sink faucets, urinals, shower heads, all kinds of water use devices. Well, going back about 10 years ago, the EPA had spent a lot of time focusing on products in the home. They say, we use a lot of water outside the home as well. Can we identify water efficient products outside the home? And so they start looking at irrigation products. And so just some background on where they move forward with irrigation products. The very first irrigation product that the EPA WaterSense program started testing and putting the sticker on was weather-based irrigation controllers. That program started in 2012. And then about 5 years later, they started putting the sticker on pressure-regulated sprinkler bodies. And then most recently, last year, they started giving the label to soil moisture-based irrigation controllers. So we're going to start talking about weather-based irrigation controllers. So in terms of EPA WaterSense, what does that mean? Well, in order for a irrigation controller to get the EPA WaterSense sticker label, it has to pass a 30-day test. Okay, so what happens is these controllers are programmed for a landscape, and they're connected to a computer, and then that computer records when the controller turns on and off, and then it uses the data it collects based on the runtime for each station over that 30-day period, along with local ET and rainfall data to do some calculations for performance. And the two main calculations it conducts are what's called irrigation adequacy and irrigation excess. And so for the controller to pass the test and receive the label, it has to have at least 80% adequacy and no more than 10% excess for all the zones tested. Okay, so currently, and I say currently, this was released, these numbers here reflect on January of 2022. So the numbers may have changed slightly over the last few months, but as of January 2022, 774 controllers had received the EPA WaterSense label. And it's a huge number. It's a big number, and a lot of people don't realize there's 774 irrigation controllers out there. But actually that 774 controllers is only available from 23 manufacturers. So 23 manufacturers have multiple models in their product catalog of weather-based irrigation controllers. So if you pay attention to irrigation products, or you're ever looking at the irrigation aisle at the store, these are those 23 manufacturers that have an irrigation product that has the WaterSense label. And you could actually go to the EPA WaterSense website, and you can look these up specifically there. That's where I pull this data from. You can go to the section on irrigation controllers, and there's a blue and green button that says find a controller, and it produces a long list with the manufacturer's names and the model numbers for you to see what products have received the WaterSense label. So all the major manufacturers have a product, as well as some new manufacturers in the irrigation industry. Now, EPA WaterSense, it does have some value in some areas. Since this is a Travis County, Greater Austin area, and we're going to talk about smart controllers here, there are smart controller rebates available in the Greater Austin area through the Lower Colorado River Authority. They offer residential rebates for using a smart controller, and I have the link here. It's not that hard to find. If you just Googled LCRA rebates, you'll probably pull up this website as well. But the LCRA will rebate 50% of the cost of a smart controller up to $100 for a WaterSense labeled smart controller. Okay, so if you're interested in getting a smart controller or upgrading your existing smart controller, that's a great idea, and you may want to make sure that your product you're choosing is a WaterSense labeled controller, because they do offer rebates, and that can help cover some of the costs of that, which is great. It does have some stipulations. If you're within the city of Austin, you need to work with their conservation program on that rebate. But if you're in the outlying areas, one of the LCRA wholesale customers, you are eligible for these rebates. Okay, so where does our program fit in? Like I said, we've been evaluating smart controllers since 2007, and our program has evolved quite a bit over that time period. And currently, we are evaluating 9 smart controllers continuously in our program. 6 of these are Wi-Fi based controllers, and 3 of them are your standard fixed irrigation, standard self-contained smart controller. And so everybody today likes these, as seems to be very interested in the Wi-Fi controllers. Those are definitely some of the newest products in the marketplace over the last 4 or 5 years. And so I have some highlights here showing what these products look like. You may have one of these at your own home, but we can see here all these controllers that we're evaluating in our current testing program. And just kind of give you an update of what this looks like. We have 2 facilities. We have here in our indoor laboratory, these are our Wi-Fi controllers here, all connected to the data logger here that records when they turn on and off. So we have records of their operation. And then we can see over here, we have our standard smart controllers that have their own sensors. So they receive no communications. They don't use the internet. They have their own weather sensor attached to them, and they use that data they collect on site to create and adjust their irrigation schedules as needed. Okay, so both these facilities are here on campus at Texas A&M University here in College Station as a part of our program. So we have these controllers here, and we program these controllers for different types of zones. And so these aren't actually hooked up to a real irrigation system, because we'd have to have so many different real irrigation systems installed in the field. We program them for virtual zones, and we have them connected to the data logger so that we can record what would they have done. And so I don't want to get into a lot of detail here of what the landscape is comprised of, but we look at different conditions. So a range of plant material from flower to turf to ground cover to shrubs. And then if we were going to create an irrigation schedule by hand, which we just learned how that process works before the break, this is all the information we would need to have. So I have here the coefficient information, the root zone depth, the soil type, the MAD, adjustment factors, how much water the sprinkler applies, its precipitation rate, and then if a slope exists. And so, well, this here, it's all virtual, so we did not use a slope on this test. But if we were going to create a schedule from scratch, do the math by hand, we would have to use all this information. However, when we go to program the controllers, we were surprised that not all controllers are programmed the same way. We can see here that of these Wi-Fi controllers, for example, of these 6 controllers, 4 of those controllers you have to actually program in a runtime and a frequency. Whereas 2 of the controllers ask a lot of site-specific detailed information, and then that calculates it for you. So if you're going to use one of these other 4 products, you're going to have to start out with a good runtime. If you just make up a runtime and a frequency, then that controller is going to use that information year round to do its adjustments. So if you give it a poor runtime to start with, then you're going to get poor performance out of your controller throughout the year. So it's important to understand how scheduling works so that you can know how much runtime, how often you should be irrigating when you program your smart controller. So again, most of the controllers in our program, we did have to enter in a runtime and frequency. Okay, so we had to do those calculations. And so here's just a snapshot of what those calculations look like. Just like in our examples, we looked up the ET for the month. We used historical data in our calculation. So in College Station, the peak ET is 7.1 inches in July. We convert that to how many inches per week is that? And then we calculated how much water is available to the plant. Remember, plant available water is a function of your soil type and how deep your roots go into the soil while using your managed allowable depletion, or your MAD. So we can see here we have shallow water, low water holding capacity to a large amount of water available to the plants. So obviously we can see here that that's going to affect our scheduling. In our flowers that have very low water available, they're going to have to irrigate very frequently, versus our larger plant material, which has large water holding capacity, they're going to irrigate infrequently. So we're able to look at daily irrigation versus 2-day-a-week irrigation versus 1-day-a-week irrigation to evaluate how well these controllers operate under different types of restrictions. And so we can just see what that schedule might look like: a daily schedule versus a 2-day-a-week schedule, 1 day a week, and your runtime per day, irrigation cycles. And we did use cycle and soak in our calculations. So how did these controllers perform? So what I'm going to show you here is a snapshot of the general performance tendencies of some of the most common controllers. Okay, and so like I showed you earlier, we programmed these controllers for 6 zones: flowers, turf grass, ground cover, small shrubs, and large shrubs. And what I have here is the recorded daily run times per each controller for 3 different landscapes. So we can see here with the Rainbird Link Wi-Fi controller here, I'll focus here on the flowers to start with. We can see here in starting here in March, it has a relatively low run time per day. We can see about 7 minutes. Excuse me. And then we can see here at the peak here in August, we hit it increased the run times on its own to about, it looks like about 26, 27 minutes here. And then we did have a few really high run times, but we saw the daily run time and adjusted it based on the weather conditions. And we can see that trend continues for different plant types. Here we're obviously irrigating very frequently, and then we irrigate less frequently with the turf grass and even less frequently with the large shrubs. But it adjusted those run times as the weather changed. Now we look at the Hunter controller, the Hunter HydroWise, or the Hunter HC is what it's commonly called now. Remember, we had to input a runtime. Well, that smart controller, it keeps the same runtime year round. It kept that same runtime year round. All it did was adjust the frequency of irrigation. And so we can see here where it irrigates more frequently and where it irrigates less frequently. And what's interesting to note here is as we look at these different charts moving forward, whenever we see these big gaps in the data, these almost every time correlate to when there were big rainfall events. So we can see here, it rains here, it got a lot of rainfall here. So it went 4 or 5 days without irrigating because it knew it got rainfall, but it kept the same runtime. It did not make any runtime adjustments. It only adjusted the frequency of irrigation as the seasons changed. Here we have the ratio. And so this is kind of a homeowner favorite controller, it seems like, available at most box stores, Amazon. And we can see it kind of takes a mixed approach here, depending on the seasons. We can see here it starts out with a very large runtime in the spring. So long runtime, but it doesn't irrigate very often. It only irrigates every few days. And then we can see here as we hit the peak of the summer, it has a shorter runtime, but it irrigates very frequently. So it knew it was going to irrigate more often, so it didn't irrigate as much. And again, we can see here these big gaps here between these data points almost always correlate to when we got rainfall. So no irrigation occurred here because it rained, these gaps because it rained, etc. And we can see how it takes these trends based on what the weather conditions are or the ET, and it adjusts its programming methodology during those different periods. We look here at the rain machine. Again, this is a controller. You can see here, very low runtime here in the spring. The runtime slowly increased into the early summer. Again, did not irrigate very much here because we got a lot of rain during this period. And we can see that it had the long run times in the summer, at the peak of the summer, with gaps when it rained. The trend continues down here, the turf grass. And what's interesting here is with the shrubs, it did not irrigate the shrub zone at all in 2021. We actually went back and checked our calculations, and based on the amount of rainfall we had and the amount of water that could be held in the root zone, that was true. You could get by without irrigating the shrubs all year round last year in College Station because there was always moisture in the soil. The soil never dried out completely. We look here at the Orbit Beehive controller, and we can see here that the trends again, different run times. Again, this controller did not irrigate the shrubs at all in 2021, and we agreed with that. Now, I want to highlight something here interesting I find about the performance of this controller when it came to the flower zones. And with this controller, it changed its schedule, and it automatically did a cycle soak. And what I find interesting about this controller is it had a high runtime. We can see here probably about 35 minutes, but then it did 3 runtimes per day. And so the first runtime was about 35 minutes. The second runtime was about 15 minutes. And then the third runtime was only about 9 minutes. So when it did cycle soak, it didn't just keep the same runtime with each cycle period. It actually reduced the runtime with each cycle period. And what that does is, in theory, it helps to where more water is able to infiltrate, because as the wetter the soil gets, the infiltration rate of the soil decreases over time. And so this controller actually recognizes that behavior in the soil. And as a result, when it automatically does its cycle soak calculation, it reduces its runtime so that more water has a chance to soak in appropriately between runtime events. Here we have the sprinkle controller. Very similar in operation to how the Hunter controller ran. It kept the same runtime we put in all year, but only the frequency changed. So it irrigated more often in the summer, less often in the spring and fall. And again, as you can see here, the big gaps, it did not irrigate when we had rainfall events occurring. And that trend continues for all the zones. Now, this is not a Wi-Fi controller. This is a standalone controller, the Toro with the ET sensor. So it has its own little temperature climate sensor that attaches to it. And that controller is installed outside. And so it's recording the outside conditions and then adjusting the schedule throughout the year. And so you can see here, low runtime in the early spring. Runtime, it actually kind of peaked the runtime here in July. And then the runtimes then slowly then decreased down here. We did have a problem with this controller on the turf grass zone. That data is still being analyzed, so it's not available to be shown here yet. But then we can see here how that performance then continued. We can see the general trend with the large shrub zone. Here we have the Hunter Solar Sync. Again, this is a Hunter controller, but this is not Wi-Fi. This has its own sensor attached to it. It actually has its own little solar radiation sensor attached to it that it uses to adjust the schedule. And we can see here, it did adjust the run times, and the gaps do correlate with rainfall events. So we can see there, the importance of what you input into the controller and how that controller operates has a long-term effect on its performance. I haven't gone to the details of that yet, but if you just make up a runtime, you have to keep in mind that if your controller keeps that fixed runtime year-round, that's going to affect your water conservation potential, but also how much water is applied to your landscape over the seasons. So when we analyze the performance of these controllers, what we did is we divided them. We took the data and we broke it down to spring, summer, fall to look at different seasonal weather patterns. And we compared the performance of these controllers to 3 factors. One is a daily water balance, which is an in-depth calculation using ET. We used a weekly water balance approach. So this is basically like if you were to sign up for your Texas ET email, if you just look at your Texas ET email every week, that's how you would look at a 7-day water balance. And then we just compared that to the actual weather data we had. So we looked at the ET and the amount of rainfall we received from the weather station, and we compared that to how much water the controller applied. So break this down for 2021. I had this in both graph format and in table format. So if you have a favorite controller, this would be the time to pay attention to what color bar it has. So we can see here the color coding of each controller here. And then what this shows you is zone 1, which is the flowers. Zone 2 and zone 3 are turf grass. Zone 4 is the ground cover. Zone 5 is small shrubs. And zone 6 is the large shrub zone. Okay. And so we can see for each zone by controller how they performed. And what I have here is 2 black lines. The solid black line is the daily moisture balance, and the dotted black line is the Texas ET summary. And so in reality, I would like to see the controllers be very close to the solid black line. But if a controller is anywhere between the 2 black lines, the dotted or the solid, it's doing a good job. It's just a change. You could look at it as a change in methodology or scheduling approach. If they're within the 2 lines, they're doing a really good job. And a lot of times the 2 lines come into agreement. There's just a few times of the year based on the zone where we see a bit of a gap occur in a daily versus a weekly approach. But what we can see here is that some controllers are putting out quite a bit more than what we calculated. Some are putting out less than what we calculated. Some are either right on target or within this acceptable range. So overall, visually, we can look at this trend and see kind of a bit more over irrigation occurring throughout these zones. Not so much with the flower zone here in the spring. So break this down, the raw data here. And here is how many inches of water each controller applied for each zone. Now, I don't want you to get too fixated on these numbers here. I'm gonna point out the important factors here. And so what I've done here is I've highlighted in yellow the zones that are doing a great job. And what this is the zones in yellow, that means that value is within 20% of what we calculated it should be in a perfect situation. So if the controller is in a yellow box, it means that amount of irrigation is very close to what we calculated was needed. And so we can see here, many of these controllers did a really good job. For zone 1, we can see 4 out of the 7, 4 out of the 8, excuse me, in the zone 1, 4 out of the 8 in zone 2. We're real close. But what's really interesting here is we move over here to the shrub zones, and we can see here that there were a few controllers that did not irrigate in the spring. So that's 94 days, 14 weeks in the early spring, where those controllers chose not to irrigate zone 5 or 6. Well, when we compare that here at the bottom to our moisture balance, we agree with that. We showed that no irrigation was needed. And why do we show no irrigation was needed? Well, we can look here at the weather data. The ET over that 14-week period was 13.54 inches. So that's the ET from the weather station. But the weather station also recorded 13.69 inches of rainfall. So we had a lot of rainfall that occurred. And this is a good sign that these controllers are recognizing the amount of rainfall that occurs and not irrigating when it's not needed. Okay. So we move into the summer months. And again, we can see that the 2 black lines here become more in agreement. So whether you do a daily calculation or a 7-day calculation, the 2 lines are very close to each other for the most part. And we can see how that varies based on the plant material. And so we can see a few of the zones put out a little bit more than was needed for the flowers. Some of the controllers put out a little bit too much for the turf. We can see how they put some were right on target for the ground cover, some are a little bit above, some are a little bit below, and that trend moving forward. Again, we go back and look at the raw numbers here. Again, don't need to get too fixated on the actual values per se, but we can look at the highlights here. And what's interesting here is we can see that one controller, it got 4 out of the 6 zones within 20%. So it did a good, I'll go ahead and say the name here. The Hunter did good for the flowers, turf, and the ground cover in the summer months. And this was a 16-week period. So 111 days was our summer gap. And then the Hunter that's self-contained, that's not on the Wi-Fi, it got 3 out of the 6 real close. Again, we could highlight zone 6. There were 2 controllers that chose not to irrigate zone 6. And our calculation shows we agree with that you could have not irrigated because the soil never dried out completely. And just to have it highlighted the weather, we can see it definitely was hotter and drier in the summer. The ET was 20 inches, but we did get 14 inches of rainfall occurring. So if you have a deep root zone in a deep soil, you can store a lot of that rainfall for a long period of time. And then we move into the fall. So we should start to see water requirements decrease in the fall. And again, we can look at the trends here. About half the controllers right here are right here between our 2 calculations in agreement. A few controllers are just a little bit more than what we calculated. So a bit of a gap here between the flower zone controllers. A couple of controllers still struggling with the turf grass, putting out a little bit more than what's needed. Ground cover was real close for some controllers. One controller just put out very little compared to what we calculated. And then we can look at the trends here with the turf, with the shrub zones 5 and 6. So here we kind of see a shift in performance now as we go into the fall. Or in the summer months, the Hunter Hydro-wise, it had 4 out of the 6 real close. Now only 2 out of those 6 are real close in the fall, but the Roccio is doing a better job. We can see here that it had 4 out of the 6 zones within 20% of our calculation. Again, seeing those same controllers not apply any irrigation in the fall. That's a 62-day period, 9 weeks long. And overall, 2021 was a really wet year. We can see here from the weather station, the ETO was 7.5 inches and the rainfall was 8.11. So we got a lot of rainfall, but that rainfall came in very heavy, unfrequent events. So you may get a lot of rainfall 1 week and then you go 2 weeks and then you get a heavy rainfall again. It wasn't spread out evenly in an ideal situation. So we did have to irrigate quite a bit, and we can see here the gaps in data, how well the controllers performed. For the most part, controllers weren't extremely excessive here. We can kind of look at some of these numbers and see where did they sit. See a couple of these controllers are real close to almost having the same amount of water applied for the flowers. And then we kind of see a drop in controllers. Some underestimated it. So those that put out about 5.5 inches in the fall versus those that only put out about 3.5 inches in the fall. So those controllers under irrigated in our opinion. Now, potentially those flowers could look fine still, but in our opinion, it does show a trend that there could be quality issues by not putting out enough irrigation for those more sensitive plants. So we've put all this together, and how do we look at the big picture of how well these controllers apply to irrigation? Okay. So what this table does is I've summarized all the data. I know this can be a bit overwhelming, but I'm trying to make it as simple as possible to highlight the big things here. So what I did here was I added up the total irrigation applied by all the controllers, and that's what this shows here. If you add up all the irrigation for the controller for the whole year, how many inches of irrigation would it have applied for all 6 zones? So we can see that here. And if we come down to the moisture balance calculation, this shows here how much we calculated was needed for the year. So for our landscape, we calculated we needed 57.5 inches of water for the year for all 6 zones. Okay. Well, we can see here, we can look at this different ways. This controller here put out 56 more inches than what was needed over the whole year. That's one way of looking at it. Whereas this controller here put out 27 inches less than what we calculated for the year. So we can look at the degree of how much a controller is putting out too much water, or could a controller not be putting out enough water to the landscape? But what we have to remember is that this occurred over the whole growing season. And that growing season last year was 39 weeks long. That's March through the end of October. 39 weeks. Or November, I think, actually, yeah. So when we divide up this differences on a weekly basis, on a weekly average, how well of a job is your controller doing? What we can look at here, we can see, well, the Hunter hydro-wise, on average, it only put out about 1/3 inch more water per week year-round. And the Hunter Solar Sync controller, which is the Hunter one that doesn't have the Wi-Fi, has its own sensor on it, it put out 2/100ths of an inch less water per week on average throughout the whole growing season. So if we look at these weekly differences here, you know, how much are you willing to sacrifice a little extra irrigation here and there? We can see some do a very good job, you know, less than an inch difference per week. A couple of controllers were over an inch difference per week. So not performing at a great level if it's going to put out 1.5 inches more per week than what's needed. And especially if you're in an area that's got very shallow root zones or is known for very hot summers, you know, or water restrictions, that could be a deal breaker for you. So if we look at 2021, where we had a lot of rainfall, we can see these 2 controllers were kind of at the top tier of performance. I'm not saying the other ones were terrible. These 2 were at the top tier. But I'm going to show you now, if we go back to 2020, the year before, same controllers, same landscape, but different weather. We can see here that in 2020, performance is a little bit different. Again, we see the hydro-wise be in the top tier. On average, only about 5/100ths of an inch more per week. But we also see the rod show did a great job in 2020, only a 1/10 inch more per week. And then we see the sprinkle controller. It only put out 0.28, about a 1/4 inch more per week on average. But if we compare the 2 years back to back, we can see that in 2020, we actually needed 81 inches of irrigation compared to in 2021, where we only needed 57 inches of irrigation. So that's two very big differences in years. We go from a drier year to a wet year, where we see a difference in over 20 inches of water needed for a landscape. And so, oops, sorry, wrong direction. So we use this information differently, and now I'm getting to some main points here in a second, but the climate is always changing year to year. Now we're moving into a very dry summer, and we really haven't had to push these controllers into a heavy drought year since we've installed a lot of these Wi-Fi controllers. The last 4 or 5 years have been average to a little bit wetter years. So we're going to get we're really looking forward to getting some good data this summer if we see this drought continue, where we see extended dry periods where the controller is going to make most decisions based on the weather without the help of rainfall. So the big takeaways is no controller was perfect. And so we continually to test every year, trying to find that perfect controller. And we haven't found the perfect controller yet. We see controllers that are at the top tier, which you saw on our list there, that are doing great jobs, but they're not perfect yet. And so we're still struggling to find that best controller out there that we can say, hey, this was going to be good year round, no matter what. And we haven't found that yet. We saw one controller did great in the summer, but then one controller did better in the fall for the same landscape. We see those inconsistencies. But what we do see, if we look at the positives of smart controllers, and we go back and we look at those daily runtime charts, is all the smart controllers are making adjustments. They're either adjusting their runtime daily, or they're adjusting how often they irrigate, which is better than having your typical controller that you just set one time and you forget, you walk away, you never touched again. So you're going to save water with the smart controller because it's going to make adjustments. Now, the amount of savings you're going to get is going to vary, obviously, based on which controller you have, based on our early data we have here. We also show that most smart controllers are positively responding to rainfall. So we saw those big gaps in data. And we saw that some controllers never irrigated those shrub zones because it recognized that we had plenty of rainfall and there was plenty of water in the soil for that plant to access that moisture. So that's a big positive there. And then we have the added benefit of with the Wi-Fi technology. What I really see being the biggest game changer in this state of the technology is with the Wi-Fi controllers. These controllers are all accessible from your phone. And so you have the ability to adjust those controllers in your pocket. I have my own irrigation business on the side. I do irrigation repairs and some mild installations. And I'm not going to pick on any homeowners here that are listening to this, but I know many times when I go to a homeowner's house to fix a system and I have to go turn on the controller, I've got to move a stack of boxes of Christmas decorations, or, there's 4 or 5 bicycles in the way of it. If I have a hard time accessing it, I know that the homeowner isn't accessing the controller regularly. And so maybe that's a reason that we may forget to adjust our controller because it gets tucked away in the garage, hidden behind something, and we don't pay attention to it. Well, with a Wi-Fi controller, and a lot of these controllers are now compatible with smart homes like Alexa and those other devices, to where you can link those together. We have that ability to say, hey, we turn off irrigation because it's wet this week, or We can adjust that, pull out our phone and say, you know what, I think we're putting on too much irrigation and adjust my run times on my phone. And so I think the biggest game changer with this technology is having that remote management access in your pocket. So that's not always necessarily a set it and forget it. If you see something happening with your yard, you always have everybody always has their phone on them. So that gives them easy, no excuse not to pull up the app, make a few adjustments, check the app, make sure your settings are correct, that it's doing what it's supposed to do. And you can have a well-performing yard and save water in the process. Okay. So with that, I'll open it up to Daphne if she has any questions for me.
Wow, again, such great information, very, very dense. So before we dive into questions, I have a broad kind of one. We talk through these smart controllers, which I'm super excited about, really excited about the data that you guys are doing on the research, giving the data that you're giving. But if someone on the call or just in our community doesn't have an irrigation system, considering putting one in, what are some of the pros and cons or things that people should weigh before deciding to install an irrigation system in their landscapes?
Okay, so if you're trying to decide to install an irrigation system, you need to have a reality check on the situation, because a lot of people I find are surprised after they get an irrigation system how much their first water bill is that a lot of water goes into irrigation. So you may not notice it if you have your little hose and sprinkler irrigating your front yard that you move by hand. You do a good job of moving that. But when you start putting in a bunch of sprinklers and it's irrigating every square inch of the yard, water use goes up pretty quick. So be in mind of that. I had a gentleman call me there this week that his water bill was $200 higher after having an irrigation system installed last month, and he thought there was a problem, but he just wasn't used to that much water being used. Second is, if you're going to have an irrigation system installed, you need to and you must go through a licensed irrigator. They will walk you through the process. Make sure you have a good design that's going to provide uniform coverage to your landscape, but also to make sure that irrigation system is zoned properly. We want to make sure that when we irrigate, we're only irrigating turf grass at one time. We're only going to irrigate the beds at one time. We see a common mistake is people try to cut cost and try to irrigate too much at one time. And the result of that is that some plants have different water requirements, and they're either going to get too much water or not enough water. So making sure you have a properly zoned landscape to where you only put the amount of water out as needed. Go back to my slides here a few slides back. If you're irrigating your flowers and your shrubs at the same time, the shrubs last year didn't need to be irrigated, but the flowers did. So if you irrigate those at the same time, you're going to be wasting water on the shrubs while the flowers get what they need. So properly zoned landscapes is one of the most important key factors, I think, if you're going to put a irrigation system in. And then be aware of, irrigation systems use lots of water. Typical sprinkler system puts out anywhere between 15 and 20 gallons per minute. So if you're running your system for an hour, you can add up how much water you're using real quickly.
That's a very good point, and something that people really should consider, because once you get it rolling, maybe you can use less water, you can understand it better, you can turn those run times back and then conserve water. But in the beginning, it is kind of a learning process to figure out how to use them, isn't it?
Yes. Mm-hmm.
Yeah. Well, I want to look back to one more thing before we move into questions, and that's the ET Network website. We are going to send you guys the link to that. And I want to encourage everyone to create a profile on that and to use that data to make more informed decisions on irrigating your landscape. Whether you have an irrigation system or not, you can use that information to see how much our area needs to be watered based on the amount that has either evaporated from the soil or transpired from plants. It's a really useful piece of information, and I want to encourage everyone to go on there and create a profile. And again, we'll send you the link. All right, we do have a couple of questions. So here's one. Do drip irrigations using drip irrigation systems, does that factor into these calculations with smart irrigation systems? So versus, a rotary sprinkler or any other type of?
The only difference between and to go back to be more specific, in our test, we assume drip irrigation of the flowers. And all that does in the calculation is it changes the precipitation rate. That drip applies water slower than sprinklers does. And that was that was taken into account in the programming and the calculation of our run times, that drip would run longer than a spray system would for that part of a landscape. So overall, drip was considered in the testing. And we envisioned that the flower zone was irrigated with drip. And so if the controller asked us what kind of sprinkler type was used, or if it asked for a precipitation rate, we entered the precip rate, or we told it was using drip irrigation. So that was considered, and it is taken into account.
When we talk about drip irrigation, we are most familiar with the kind that we put in on top of the soil, maybe under our mulch, and water our flowers with. We didn't really touch too much on subsurface drip for turf grass. Is that still being used? Is that still a technology that's gaining in popularity, or has that kind of waned and it's being used less?
It depends. We do see drip still used quite a bit around the state. I'm not sure that the trend specifically in Central Texas these days, but where we see people like to use drip is in areas where we have deeper soils. You can irrigate deeper root zones. It can be a real challenge if you have shallow roots, shallow soils, to use drip, because you don't have a lot of room to store that water. And then just the installation of that can be a real challenge if you're working with a lot of rock and trying to get that installed deeply. It increases cost quite a bit. But we continue to see drip be very popular in bedded areas, and we still see drip used in some turf grass applications. We do have state rules that dictate where we can and cannot use sprinklers. Some of you in the Austin area may be familiar with some of these rules. Austin has more stringent rules. And if we talk about, areas between sidewalks and roads, those areas these days are predominantly irrigated by drip irrigation, because by state regulations, you're not allowed to irrigate those areas with sprinklers anymore. So we see certain parts of the landscapes where drips become common practice. But as far as whole turf landscapes being drip, it varies significantly based on goals and reasons why they want to move to drip, depending on where you are in the state.
All right, we have one last question about restrictions. So we talked about watering restrictions, and we have these smart controllers that can plug into weather networks and make decisions about when to irrigate and when not to irrigate. So can these smart controllers be manipulated? Can they be programmed to follow water restrictions and weather data, not just weather data?
Most smart controllers do have a setting for water restrictions, to where you can limit frequency days, or you can actually impose some specific water restriction window into them. We kind of saw that a little bit in our testing program, because we did limit 3 of the 6 zones to 1 day a week. That was a natural decision that we put on those zones. But specifically to the question of use of weather data and restrictions, each manufacturer follows a different scheduling methodology. There really is no consistency in how they use their weather data. And not all manufacturers use true ET. On top of that, some calculate daily ET, like I showed you, and some use historic ET that is adjusted by current temperature or other weather factors. So the way they adjust those schedules varies, that not everybody uses the exact same methodology. And part of that is patent issues, part of that is cost programming considerations and taken into account for the product and how it's developed. But yes, you can. The short answer is yes, you can put water restrictions on those controllers. The water restrictions can, depending on the manufacturer, they can incorporate the weather data as well, but not all handle that information the exact same way.
Very good and helpful information to check out those controllers before you purchase one, so you understand that you can use it or not to your best advantage on your system. Well, just to wrap up, the information that you've presented often makes people feel a little intimidated by the technicality of it, all the numbers, the calculations. Just to kind of summarize for people who their heads may be spinning right now, what of your information that you presented, how can people digest it most easily, or where can people kind of start to get familiar with these concepts and use them in a home landscape?
Okay, there's two simple ways to do this. And to start with, if you have an irrigation system, the key to managing your irrigation system is going to be to understand how your system operates. And in order to do that, you really need to know how much water your system applies. If you have spray zones, if you have rotary zones, if you have drip zones, all those different zones apply water at different rates. So there is no magic runtime that fits all three scenarios. A spray zone will apply 3 times more water than a rotary zone almost always. And so if you have a 15-minute per day schedule, that means 3 very different amounts of water being applied between drip, rotors, and sprays. So you really need to understand how much water your system uses. And you can go out and do a catch can test. You can contact a licensed irrigator, or you can actually just go online and look up the manufacturer of your sprinkler on their website, and you can look up what the precipitation rate of their sprinklers is, and that'll give you a good estimate. And if you know that your sprays will put out 1.5 inches an hour and your rotors will put out 0.5 inch per hour, then you can use things like Texas ET, where you can see, okay, I need 0.5 inch this week, or I need 3/4 inch this week. Is my runtime close? You don't have to go out there and change that runtime every Monday or every Tuesday, whatever your watering day is. But you need to make the big changes. If we're looking at, this week you may need 12 minutes versus next week you need 13 minutes, you're probably fine. But if we're looking at 12 minutes versus 25 minutes, we go out and we make those adjustments. And you need to, in order to make those adjustments, you have to understand how much water each zone applies versus how much it needs. And if you understand that, then you can better manage, the excess, which will save you water. You don't want to have excess, but then you can also get you a little bit more involved operating that system. You can tell if you run it too long, does runoff occur down your street? You don't want that happening. And so high precipitation rates are a leading cause of runoff, because high precipitation rate with too long of a runtime just exceeds how much water can be infiltrating the soil within a certain amount of time. So get out and look at your irrigation system, see how much water it applies. It can be as simple as taking a coffee cup out there and putting it out there and seeing how much water you get in 5 or 10 minutes in your coffee cup to give you a rough idea. And then, when it rains, turn off the irrigation system. We don't need to irrigate every week year round. We have plants that the plants we have today came from somewhere. And we go back 100 years, and we have trees in Central Texas that are historic trees that were not irrigated 100 years ago that are doing great. And so you don't have to irrigate your tree every week. They can survive off, what's in the soil and a little bit of rainfall. You maybe just give it a little bit of help every now and then if we get into the worst times of it. And then just go out and check your irrigation system as well. Our irrigation typically runs at night or early morning before we get up and go to work. And just turn it on, look at it, make sure you don't have obvious problems with it. And so just get to know your irrigation system, as there's probably a key takeaway. Know how much water it applies, how should it be running, and just looking at it and managing that way can help you save a lot of water and maintain a good landscape in the process.
All very good points. Well, thanks everyone. That's all the time that we have today. We'll follow up individually with any unanswered questions that we didn't get to. Thank you, Charles. I really appreciate the depth of your knowledge regarding irrigation and your dedication to conducting the research that's critical to water conservation in our communities. And thank you to our attendees for participating. Very soon, you'll receive an extensive email from us, including a link to a short survey, and we'd really appreciate if you filled that out. Your feedback will help to ensure that Extension can continue to offer these types of valuable programs in the future. That email will also include a link to access the recording of today's session. You're welcome to listen back to it as many times as you like. We'll also have a list of resources for further study and links to any websites or source material listed by Charles today, along with information on how to contact us our gardening helpline and ask any questions that you'd like, as well as to subscribe to notifications for future seminars on water-wise strategies for Austin gardens, and also horticulture and gardening information in general. Until next time, thank you for joining us and happy gardening.